we had div A equals rho. We have a problem, this is a function, this is a vector. You need to give me something more information, otherwise I can't find out all three components of this vector.
Right.
How am I going to find A? This is the field equation for A. So the field equation div A is equal to rho, and all I'm given is rho on the right-hand side. I have to find A, and A is a vector, and all I'm given is the divergence of A. If my divergence of A gives me all the information I need to specify A, that given this equation, I can find A from this equation, then it means that I don't need to specify a fully general three-dimensional vector. It's a very special kind of three-dimensional vector, where I only need to specify its divergence to tell me the whole thing. Okay. Now, there is a theorem, Helmholtz's theorem. I'm not going to prove it here. You can see it in a quick book on vector calculus. That any vector can be decomposed into two pieces: the gradient of some function plus the curl of some vector. Or be usually a magnetism, so I don't want to confuse. Take any vector. You can decompose it into two pieces. Okay, two vectors. These are both vectors. This is a vector, and this is a vector. All right? One piece of the vector will be the gradient of f. I'll explain what that means if you haven't seen it. And the other piece can be the curl of some other vector. There's always a vector c and a function f, such that the curl of the vector c and the gradient of the function f together will give you that vector A. Any vector A can be decomposed into these two pieces. Take any arbitrary vector with three components, the I, j, and k, x, y, and z, r, theta, and phi, whatever. There's some other vector c and some function which you can create this equal that. Now what are these things? This we saw, this little triangle thing. It is an operator which was, for rectangular coordinates, it was the derivative with respect to x plus derivative with respect to y plus derivative with respect to z. This is an operator, derivative of x, derivative with respect to x in the x direction plus derivative with respect to y in the y direction plus derivative with respect to z in the z direction. This triangle thing was the del. Operating on a scalar function, we call it the gradient. This is the gradient. This alone is the gradient.
Right.
Okay? Now I'm going to operate with the gradient on operating on a vector. So you have the vector, let's say, x component plus a y component plus a z in the z direction. Okay, this is a vector ax in the x direction plus ay in the y direction plus az in the z direction. This is just an operator. What we did is divergence before. If I operate on the vector A as a dot product, dotting this operator into the vector A, where this is the vector A, so I'm dotting this operator into the vector A. Okay? This was just the operator, and I can do various things with this operator. I can dot it into, it's a vector operator, I can dot it into another vector. I dot it into this vector. How do you dot product? You simply take this times this, plus this times this, plus this times that. That's the dot product. So it's derivative with respect to x of ax, plus derivative with respect to y of ay, plus derivative with respect to z of az. That's simply what it is. Derivative with respect to x of ax, plus derivative with respect to y of ay, plus derivative with respect to z of az. It's a function. We've taken two vectors, a vector operator and a regular vector, dotted them into each other, and produced a function. Okay? Not a vector, just a function. Dot product of two vectors. I can also take the same operator and operate on a scalar function. Not dot product into a vector, but I can, I'll write it down below so you can see the two of them together. Okay? I'm going to take the same operator, this div operator, and instead of multiplying it with a dot product on another vector, I'm going to operate with it on a scalar. So I'm going to take this thing and operate on f of r. Tell me what it is. Okay?
It's just that one.
Well, not f of r, some function of x, y, z.
Yeah, it's just the differential of that with respect to...
The differential of this with respect to x, right? This operating on this will give me differential with respect to x of f. This operating on it right? Derivative with respect to y in the y direction operating on this will simply give me derivative with respect to y of f. And this part, derivative with respect to z in the z direction operating on it will simply give me plus derivative with respect to z of f. Now, is this a vector?
What's the
Okay.
vector? No, it is a vector.
It is a
It
vector.
is a vector.
Because this thing is a vector.
X hat.
I have the x hat over here. So I have to put in x hat, y hat, and z hat.
Right.
Okay? Derivative with respect to x in the x direction of f gives me derivative with respect to x of f in the x direction. Derivative with respect to y in the y direction on f gives me this in the y direction the same. So I have three little vectors, which makes a vector. Sum of these three, the x and the y and the z. So I've taken this gradient operator, I've taken this operator, operated on a scalar, and turned the result into a vector.
Right.
Okay? I've taken the same operator and dot product it into a vector, right? And a dot product turns it into a scalar. I can also vector product it with a vector. And that will, of course, give me also a vector. This is called curl. This is curl. Okay? This is called gradient. And this is called divergence. All right? It's the same operator. Dot product is divergence. Operating on a scalar is gradient. Cross product, vector product is curl. All right? Now, it turns out that any vector can be decomposed into the gradient of a function, like this thing. There's some function f where if you do this to it, stick it here, and there's some vector c that if you do this to it, right, you have to do the vector cross product over here, I'm not going to bother, you can see it in any textbook, right? You do this to it, you add the two up together, right? This is what, a vector or scalar?
That's a vector.
This is a vector, right? This is a vector or scalar?
Vector.
This is a vector. So you have two vectors here. You add these two. This is three components, this is three components. You add them up, you get a three-component vector. You get one vector. That's the vector A. You have to carefully choose your F, carefully choose your C, but any A will give, it'll be possible to do this. Okay, it's a very nice theorem. This tells you a lot of things about physics, like in electromagnetism, Maxwell's equations, so you can immediately see a lot of things kind of coming out of here. Now, what I have here is the divergence of a vector. All right? So I'm going to put it like this: divergence of A. Divergence of A meaning dot product into A. So it's going to be dot product here and dot product here. Correct? All right, so this is. Now, tell me about this. Can you easily calculate this?
Divergence
Of curl.
something like 0,
Y. Correct. Y.
because the divergence of a curl is always 0.
Y.
Some theorem which I...
Okay, but it's very simple to see. If you take this seriously as a vector, a cross product of two vectors points in what direction? Right, perpendicular to the plane. This cross this goes perpendicular to the plane.
Right.
In other words, this vector is perpendicular to this operator. A dot product of a vector with a vector that's perpendicular to it is 0 by definition.
Right.
So if you take these seriously, and they do work like that. So this is perpendicular to this del, and this dotted into something perpendicular to 0. So this right away vanishes. So in other words, if you take the divergence of some vector A, right, it can always be made equal to this thing, del dot del. Now what is del dot del? It simply means take this thing, let's say, and dot it into itself. Right?
Right.
What would that give you? Let's take that thing and dot it into itself. Derivative with respect to x in the x direction plus derivative with respect to y in the y direction plus derivative with respect to z in the z direction. Over here also, derivative with respect to x direction plus derivative with respect to y in the y direction plus derivative with respect to z in the z direction. And we're dotting them into each other. What do we get?
Del.
You're going to get derivative with respect to x of derivative with respect to x. What happens to these vector things? Well, it's a dot product, so
That's just x.
x hat dot into x hat is just 1.
Alright.
So you have here derivative with respect to x of derivative with respect to x. And here, derivative with respect to y. Now, is it times, what is it? What do I write? How do I write it?
Plus.
Plus. That's simply how you dot product. This times this, plus this times this, plus this times that. So it's derivative of x plus derivative of y plus derivative z. Second derivative. So it's basically second derivative with respect to x plus second derivative with respect to y plus second derivative with respect to z. All right? So we label it del square. Whatever, just notation. It means operate with del and then operate with del. Okay, it's really div of del operating on something. It's always going to be the second derivative plus second derivative plus second derivative, and it's going to operate on something. It doesn't stand by itself. It's always.
Oh yeah, it's not correct. Oh yeah.
Pardon me?
So that would mean that A is a.
So that's this thing here. We did del dotted into itself. That's del squared. So it's this operating on f. So this operating on f is simply this operating on f, which is simply second derivative of f with respect to x plus second derivative of f with respect to y, which is a function. In other words, if we take the divergence of any vector, we can certainly express it as the del square of some function. There is some function f such that if you take its del square, right, this will probably del square, there's some function f, if you take its del square, it will tell you what the divergence of the vector is. Okay? Now what this means, conversely, is if you're telling me that div A is totally specified by some scalar function, how could it be? It can only be if what? How could it be that there's a vector that the div tells me everything?
That there's a potential.
What do you mean? Where does the word potential come in?
The gradient, basically.
Well, let's go step by step. If this is sufficient, if div A is equal to rho, if that's sufficient, right? Div A, this vanishes. Whatever vector it was, right? Doesn't matter, only this is left. That means that the only part of the vector that I need is del square f.
Well, there is a del squared f, which is rho.
So, in other words, if div A, now let me write it over here, div some vector A is del square f. That's basically what I'm saying.
Right.
My div A, I don't have this, I don't need it. It's just del square f, because I can always decompose A into two pieces. One piece will vanish when I do the div. So div A will be del square of the appropriately chosen f. Del square is what? Is div, is this, right? So what does that tell me about A?
A is the gradient of.
A is equal to this. Okay? So what I learned from this is that this A is such that there is an f which can be appropriately chosen such that the gradient of that f specifies A entirely. Again, why? I started out by saying if my divergence of A gives me all the information I need to specify A, that given this equation, I can find A from this equation, because otherwise, how am I going to find A? This is the field equation for A. So the field equation div A is equal to rho, and all I'm given is rho on the right-hand side. I have to find A, and A is a vector, and all I'm given is the divergence of A. Then it means that I don't need to specify a fully general three-dimensional vector. It's a very special kind of three-dimensional vector, where I only need to specify its divergence to tell me the whole thing. From Helmholtz, we know that the vector A, like any vector, can be expressed as a gradient of some function plus the curl of the vector, which then means that the divergence of that vector will give me the del square of f. This comes out to 0. And therefore, what it's telling me is that divergence of A is obviously just the del square of this carefully chosen function. Since del square is div grad, that means that A is grad f. In other words, in order for this to be sufficient, div A equal rho, for that to be a sufficient field equation in itself, it must be that this vector A is of the special type that it is in fact the gradient of some scalar function. Okay? So these equations kind of imply each other to some degree. We can now write them together. Div A equal rho by itself is not sufficient to specify A, but if I tell you that A is the gradient of some function, let me call it now the specific function phi, give it a name because that's what they usually use, this is enough now as a field theory. Div A is equal to rho, where A is the gradient of some function. Say, oh, okay, because otherwise I wouldn't be able to, div A is not enough. Now I can combine these two. If A is the gradient of phi, I can stick it in here, and I'll have div grad phi equal rho. But div grad, remember we just did that over here, div grad was del square. So we can just write this instead of div A is equal to rho and A is equal to grad phi, we can write A is equal to del square phi. It's the same thing. There's a little bit more information in a way contained in these two equations together, this set of equations. This tells us a field equation. The right-hand side, the left-hand side with matter and acceleration and so on. And this tells us about the substructure of A, which allows us to have only this one field equation be sufficient. Okay? So now we can see in a very nice, like, vector calculus way what it means that A is the gradient of a phi. Now, why am I laboring so much over this? For two reasons. One, because in ordinary gravity theory, when you taught it in your first course, the potential is like kind of like, what's the importance of it? What do we have as the potential? You're told the acceleration is gm over r squared, right? If it's a vector, then it's, you have r hat over here. And that is equal to the gradient of the potential. But maybe let's say v, all right? And what is v? V is basically 1 over r, gm over 1 over r. Big deal. I mean, the derivative of 1 over r is 1 over r squared with the sign change. So what? Big deal, right? You know, what's it? So it turns out you can do all kinds of tricks, energy calculations and stuff like that. It's very nice, but it doesn't have a real significance. The significance is geometrical over here in terms of the vector calculus. And we'll now go see some more geometrical significance of it.